So, John, can you hear this noise in the background?
Yeah. I'll mute and see if it goes.
Well, I don't hear it now, but I'm not sure what that means.
Well, let's hope it doesn't reappear during your talk.
Well, thank you, Jennifer.
How are you doing?
Doing good here, yes. Yeah. Well, that's a fantastic talk.
Oh, thank you. Thank you.
So, Umberish.
Yes, ma'am.
Are we ready to go?
We are all set to go.
We're all set to go. So it's my great pleasure to introduce Bill Halperin. He's going to tell us about superfluid helium-3 from the vantage point of somebody who was there from the very beginning. So looking forward to it, Bill.
All right. I'm going to share a screen. John.
Yeah.
Will you let me know if you can see my shared screen?
Yeah, I could see your shared screen a moment ago. I can see it now.
Excellent. Okay. Well, it's my great privilege to have the opportunity to participate in this special session of the Quantum Fluids and Solids conference here in Bangalore, QFS 2021. I'll tell you a little bit about superfluid helium-3. As John mentioned, I have a perspective going back a while. I'm going to highlight some of the contributions from my students and postdocs in green. The story begins over 100 years ago. That was mentioned earlier. Kamerlingh Onus liquefied helium, and when he reduced the pressure, there was cooling that took place. It wasn't easy to measure at that time, but somewhat later, a similar kind of cooling was predicted by Pomeranchuk. He had noticed that the melting curve of liquid and solid helium-3, the rare isotope of helium, was such that if you pressurized it has a negative slope, that would produce cooling as well. And this was really Dave Lee's inspiration at Cornell in the late 60s to pursue this approach, and I'll explain why. The trace then of increasing the pressure and therefore obtaining cooling of some form, it wasn't precisely measured back in those days. This is in late 1971 and 72. But sharp changes along the pressure time trace indicated that something was happening, labeled A and B by Doug Osheroff. And if you apply a pulse of heat while the liquid and solid helium are on the melting curve, it's very interesting that you see two time responses. One is very short, associated with the liquid, and the other is very long, associated with the equilibrium established between liquid and all of the solid. There's almost 3 orders of magnitude difference in time. I'm pointing this out because this is extremely important to the interpretation of this pressure time trace, which is the discovery of superfluid helium-3. It has to do with the fact that the thermodynamic system is really that of the liquid in a complete equilibrium with a thermodynamic interface with the solid. This was first noted, by the way, by Vidensky at the Kapitsa Institute back in 1972, in the very earliest days of the interpretation of this trace. And in fact, the fact that there's a thermodynamic system of liquid helium-3, superfluid helium-3 then, and an interface with the solid was exploited by Dennis Graywall, and with major contributions from Dwight Adams' group at the University of Florida, inventing the melting curve thermometer. So let me come to what happens in the phase diagram, pressure versus temperature. The A and B features that I had mentioned previously are along the melting curve, which is rather flat and not observable in this trace, but it would be this point that I'm showing here and this point here to the left. But this phase diagram was rapidly filled out by John Wheatley's group, Olli Lounismäe's group in Finland, and even to the present day work on this phase diagram is being pursued, for example, in a recent letter by Jivak Parpia's group at Cornell. So I want to come back to this challenge. That's the challenge of actually measuring the temperature. You can know from being on the melting curve, if it has a negative slope, that increasing the pressure decreases the temperature, but by how much? So at Cornell, it was prescribed that this Clausius-Clapeyron equation, which describes the slope of that equilibrium line, could be inverted and expressed in this way. And it's interesting to do so since measurements of the volume of the sample and measurements of the heat pulse which is inserted, and doing this measurement as a function of pressure between, say, 2 points, a reference point and pressure P, integrating gives the ratio of temperatures between those two corresponding points. This is actually the Kelvin definition of temperature. And if you use this definition of temperature, it's a thermodynamic temperature, you can measure the heat capacity of the liquid helium-3. Remember, it's the liquid helium-3 which forms the thermodynamic system in contact with an interface with solid. Once you have the heat capacity of the liquid helium-3, then you can go back to the Clausius-Clapeyron equation and have calculated the entropy of the liquid helium-3. The molar volume differences are well known, and therefore you can extract from the measurements, again, in the same temperature scale of the slope of the melting curve, you can extract the solid entropy. And there, a rather interesting thing happens. At somewhat lower temperatures along the melting curve, again, it's flat on this scale, something happens here around 1 millikelvin. What happens is that the entropy shown here in the inside of the top figure drops suddenly. What I'm showing on the right-hand side in the main figure is actually the measurements of heat inserted and the corresponding volume change to measure for a measurement at a constant pressure. And those measurements indicate directly this decrease in the entropy. That entropy was then reflected in the properties of single crystals of solid helium-3, which I'm going to tell you about in just a minute. But to complete this early discussion, the Pomeranchuk cell that achieved these results is shown here, where liquid helium-4 is used as an inert hydraulic fluid, and the displacement of capacitor plates measures the volume, and similarly, capacitor plates at the bottom measure the pressure. Now back to Doug Osheroff's measurements on single crystals that were created down here in the ordered antiferromagnetic state. It was indeed the observation of principally 3 domains in the spin wave spectrum, 3 domains in a single crystal, I should emphasize, interpreted by Mike Cross and Danny Fisher, and together they reached the conclusion that the antiferromagnetic state was a so-called up-up, down-down state, essentially uniaxial, and that was confirmed in the tour de force measurements of neutron scattering by Jacques Fluquet and Schweitzer in Grenoble in the CEA. Now, that's not the way refrigeration is done today. I warrant that there's not many Pomeranchuk refrigeration tools being used. Rather, it's nuclear demagnetization, which is the powerful way to cool superfluid helium-3 to extremely low temperatures. And here I want to just mention that the adiabatic demagnetization, say at Northwestern, using the coolant praseodymium nickel 5, can hold below 1 millikelvin of temperature for a period of time of 30 days. This is the sample cell, which I'm showing for illustration. But I did mention the melting curve thermometer earlier, and the validity of the melting curve thermometer is precisely this argument of the thermodynamic system, which is in play. And for a melting curve thermometer such as this one at Northwestern, I'm showing you the transition on warming from the superfluid B phase to the superfluid A phase. And there's clearly a latent heat here, which was measured in the early days. And if you use that latent heat together with the amount of helium-3 that's in the melting curve thermometer, you extract that the heat leak is 10 to the minus 10 watts. That is a tenth of a nanowatt. So coming back then to the phase diagram, A and B phases, I want to emphasize, as Professor Kono has pointed out, the symmetry of these 2 phases. There are characteristic symmetries, and it's important to have a scheme experimentally to make demonstrations of those symmetries. So the A phase has been discussed by Professor Kono, and in work that they have done at RICAN, they show that the characteristic symmetry, which is broken time reversal symmetry and chiral symmetry, is manifest. And I'm going to come to that in a minute or so. Now for the B phase, interestingly, it's an unusual relative broken symmetry. It's the broken relative spin orbit rotation symmetry. And of course, it's time reversal symmetric. And the pictures are those of the energy gap around the Fermi sphere. I want to emphasize that this broken relative spin orbit rotation symmetry, which is really the characteristic symmetry of the B phase, or broken symmetry of the B phase, that has nothing to do with the dipole interaction. It's not, the dipole interaction on this scale is negligible. Now, in the early days, long before the discovery experimentally of superfluid helium-3, Balian and Wertheimer predicted that that B phase was the stable ground state. And independently at the Kapitsa Institute, Verdovin came to the same conclusion. But interestingly, even back in 1963, Verdovin characterized subgap states. Here I'm showing on the left-hand side that the gap of 2 delta per Cooper pair has, I'm showing 2 subgap states at sort of magic numbers of square root of 12/5 and square root of 8/5. That was calculated specifically by Verdoven. And it was calculated in what's called weak coupling theory. And furthermore, it was identified that the total angular momentum is a good quantum number for the B phase, and again, neglecting the dipole interaction, and that in particular, these subgap states have total angular momentum too. The square root of 8/5 state is a subgap state that involves the real parts of the order parameter of the 18 component order parameter of superfluid helium-3. The square root of 8/12 involves the imaginary parts. For that reason, this one down here, the 8/5 is considered, is called the real squashing mode, and this one up here is called the imaginary squashing mode. The discovery of this lower one shows up at appropriate frequencies and temperatures as a really narrow spike. So there's going to be some spectroscopy that's relevant here. And the discovery of this 8/5 state, this subgap state, was made simultaneously at Cornell. And I'd like to specifically mention our chair of session, John Saunders, who participated in this process. And then again, at the same time at Northwestern with my colleagues, students and postdocs shown in green. However, how about this square root of 12/5 state? Well, that you can't see in this scale over here on the right. It's just so strongly coupled to density so that the attenuation of sound will not be able to follow this entire mode, this subgap. However, under different conditions, you can see that square root of 12/5 mode, the so-called imaginary squashing mode. And this is work I'm taking from Ling, Saunders, and Dobbs at the University of London. It turns out that in this trace, you can see 3 of the important subgap states, one of which I haven't mentioned yet. It's a J=1 state. This was the discovery of the J=1 mode that I'm showing here at the left. And then the sharp one that I'd shown previously, it shows up in comparison as a rather small blip. Now, if indeed this J=2 set of states, which can be thought of as bosonic Higgs modes, with a total angular momentum of 2, you might anticipate in the presence of a magnetic field that you'll see a splitting. And indeed, shortly after the discovery of this 8/5 mode, Avenel and Verico and Ebizawa in Paris showed this beautiful 5-fold splitting of the attenuation peaks in the superfluid helium-3 B phase. And simultaneously with that, I think within months, the theoretical explanation for these 5, actually the observation of this square root of 8/5 state was made by Koch and Wöfle, because it's part of the real part of the order parameter of superfluid helium-3b, and it couples only to spin. It wasn't thought, first of all, that might be the explanation. However, it was showed by Koch and Wöfle that indeed that's the explanation. Now, going a little bit further, as was mentioned earlier in our session, the Ginzburg-Landau theory serves as the base for trying to interpret properties of superfluid helium-3, but it's rather restricted just to the very near region of TC, that is to the normal to superfluid transition. But it is possible to calculate and to make measurements of the deviations from these numbers that I've given you, square root of 12/5 and square root of 8/5. And these correspond to the corrections to the Higgs mode masses. The context involves a free energy expansion where the 5 fourth order invariants of the superfluid order parameter, the beta 1 to 5, represent the strong coupling, where the values of beta 1 to beta 5 deviate from the weak coupling values that were the ones that would be relevant to the original predictions that superfluid helium-3b would be the ground state. Taking into account those strong coupling interactions from the calculation of Wyman and Sahls, a comparison with experiments can be made, and a summary of those comparison of experiments is given by Choi et al. Back some time ago in PRB. But interestingly, Sahls and Mizushima did calculations of the dispersion of these modes with additional precision, correctly including the F-wave pairing interaction, as well as the Fermi liquid parameters that are necessary and strong coupling that I've mentioned up here. And in so doing, the F-wave pairing interaction can be extracted, and I have to define that. It's expressed, it's kind of a funny thing, x3 to the -1. It's an expression in terms of the pairing potentials of the P-wave versus the F-wave pairing interactions, and can be expressed in terms of effective ratio of the transition temperature for F-wave superfluidity if there was no P-wave superfluidity, and that turns out to be 90 microkelvin. But more interesting, I think, is that the spectroscopy of these subgap states, the so-called collective modes, agree from both the square root of 12/5 and square root of 8/5 states to be consistent in the prediction of the F-wave interaction parameter. And this was done just recently in my group by Menuhin and Andrew Zimmerman. Now, for that to have been successful, that comparison between those two modes to predict the F-wave structure, the F-wave pairing potential, it's essential to be able to extend the Ginzburg-Landau theory. It must be extended beyond just this curve of the normal to superfluid transition. And that extension is based on calculations earlier by Serene and Reiner showing that the strong coupling interactions scale linearly with temperature, and together with these observations, Wyman and Sahls were able to make the prediction for the first time of an important property over here on the right, that is the transition from the A phase to the B phase, and the theory and the experiment are exactly right. This extension of the GL theory to temperatures well below TC is extremely useful in trying to interpret properties of superfluid helium-3 in adjusted or modified phases, such as in aerogels or in small slabs. I want to come now to this question I alluded to before. What is the basic symmetry of the B phase as manifest in experiment? I had said previously that it's the relative Rokun symmetry of spin and orbit, but here is an unusual and I think important discovery, that of transverse sound. And let me go back a little bit to the calculations of the famous Lev Landau back in 1957 with one of his papers on Fermi liquid theory, where the prediction that transverse sound could exist in the Fermi liquid. And by the way, there is no transverse sound in water. There's no transverse propagating sound in any liquid or gas, at least classically. However, there was a prediction by Landau that it should exist in a degenerate Fermi liquid under the circumstances, correct circumstances for the Landau parameters. It was thought at the time that of superfluid helium-3's discovery that this transverse sound would be Landau damped and would not be observable in the superfluid, but that was incorrect. Moores and Sahls in 93 showed that off-resonant coupling to this square root of 12/5 mode that I had talked about before gives stability to transverse sounds as a propagating mode, at least theoretically, in the narrower region between the square root of 12/5 subgap mode up to 2 delta. And following this, I have to give substantial credit to Yoon-Suk Lee in my laboratory, who as a student and then postdoc said this is what he wanted to do. And indeed, set up a cavity, 30 micron cavity to minimize Landau damping and hence observe the attenuation of sound, and discovered the existence of transverse sound. And that transverse sound I'll explain here in this actual representation of the data with a background subtracted, which exists between square root of 12/5 delta and 2 delta, where that can be spanned by changing the pressure conveniently. And what you see when you measure when you vary the pressure, thereby varying the speed of the transverse sound, you can see cavity waves through the entire region of stability for transverse sound. But they're not simple. Actually, in the absence of a magnetic field, it's a simple envelope of these fantastic oscillations of the cavity resonances in the 30 micron cavity. But when you apply a magnetic field, interestingly, then these modulations show up and they correspond to Faraday rotation, because transverse sound, just like light, will exhibit, according to the theory of Moores and Sols, it will exhibit the phenomenon of rotation of the polarization of the transverse sound, which is to be about in this direction as it propagates to the other wall of the cavity and back again. That is the Faraday effect. And it relates directly, and this is the most important point of this slide, to the structure of the orbital of the order parameter of the superfluid helium-3b phase, which connects spin to orbit through a rotation matrix. And it's precisely this connection between spin and orbit where the spin is controlled, of course, or coupled to the magnetic field, and the orbit is the transverse, and the orbital degrees of freedom are the variations in density, and that gives rise to transverse sound. So transverse sound is a direct manifestation of the symmetry of the B phase, the broken symmetry associated with the existence of connection between spin and orbit. Oh, I mentioned in passing that Charles Collett and my group, they've measured rotations of the transverse polarization up to 1,700 degrees, rather fantastic in this 30 micron cavity. And the dispersion for sound, which comes from the Moores and Sols theory, here's the frequency of the sound and the square root of 12/5 mode, which diverges as you approach the square root of 12/5 condition, and there the sound velocity diverges. And the sound velocity diverges in a manner, experimental measurements are the red, and the green is the calculation from the dispersion relation. It's absolutely fantastically consistent. However, the attenuation, which comes from the same dispersion relation, not so much, and the red data show, in fact, the measurements of the attenuation that were performed by John Davis. And the expected behavior from the calculation is shown by this brown curve. The difference between them is this green excess. It's rather substantial. And this is attributed to Andreev bound states, which we heard a bit about from Professor Kono's talk. These bound states in the B phase of superfluid helium-3 are responsible for this additional attenuation. It's not the only way in which the Andreev bound states in the superfluid helium can be observed. And here I'm going to tell you about measurements of the heat capacity that were performed by Choi in my group, Hyun-Sun Choi. And what I'm showing you is the deficit in the heat capacity relative to that that's expected from the bulk of the helium-3 shown in this square here, figuratively on the right-hand side. However, in the near vicinity of a surface, there's a region in which these bound states exist, which scales with the coherence length by a factor, I'll call it alpha. And through the measurements of the deficit to the heat capacity just below the transition temperature, you can get a measure of that alpha. How big is this region of bound states? And the results for alpha from those experiments, together with experiments that were done in Mamiya's group and by Dennis Graywall, these two solid symbols are rather consistent. And that's amazing because they cover a wide range of a factor of 3 in surface to volume areas. So that specifies the range, the physical range of the Andreev bound states relevant to this heat capacity measurement. We've heard extensively about the beautiful experiments from RECAN that Professor Kono has discussed, which are a manifestation of broken time reversal symmetry in the A phase. I like this little sketch. It will serve to summarize the mobility measurements that give rise to a Hall effect, an anomalous Hall effect. The angular momentum is pinned to a free surface shown in blue as a plate. Either the angular momentum is perpendicular, it is perpendicular, but it's either up or down relative to that surface, and depending on which one it is, then the mobilities that are measured through this kind of standard Hall arrangement is either to the left and to the right. And this diagram of the theoretical skew scattering, which is relevant to the direction of that angular momentum, is biased in one direction or the other, and the various pads that collect the mobility of electron bubbles just below the surface gives rise to a manifestation of this broken time reversal symmetry associated with the angular momentum in the A phase pinned to the surface. The theory was shown by Professor Kono, and I'll just refer to that one more time, by Shevtsov and Sols, where the theory given by Green agrees remarkably well with the experiment. I want to turn now to another phenomenon, which is very interesting in superfluid helium-3b. This has to do with high phase coherence in the NMR precession of the helium-3 spin, nuclear spin. It's been termed the homogeneous precession domain, and it pertains to the discovery of the homogeneous precession domain and the theory. First, the experiment from the Kapitsa group, Borovik, Romanov, Bunkov, Dmitriev, and Mukarsky, and in back-to-back JETP letters with Igor Fomin's theory for the same. So together, you get the following picture in which, after an excitation of the nuclear spin, tipping the nuclear spin by some angle, then a phase separation takes place where precession of the nuclear spin magnetization takes place in a coherent phase, shown in this top part of a figure I took from Bunkov's review article, completely in phase, and at a frequency given by the domain wall that separates the relaxed and the unrelaxed precessing helium-3 spins. This is a quantum state of a macroscopic amount of helium, which is in a single quantum state to the extent that they're locked together, and that's by very fast spin currents, supercurrents. Now that phenomenon of the HPD, hints of it were found in the early days and was explored in some measure by Cortini and Ashraf at Bell Labs. But this story that I'm telling you was really developed at the Kapitsa Institute, and there are applications of this, and it was shown that even in non-cylindrical sample arrangements such as this one, that there's trapping in a texture, say in a flare-out texture in a small diameter tube, and in combination with a minimum in the magnetic field, this flare-out texture can produce a bubble of the HPD right here. And that's a beautiful idea, and it was exploited to great advantage, as I'll show you in the next slide. This was done in Finland with the collaboration with Bunkov and others that I'm showing here. Now, the time scale for this precessing state, if you wish, T2, the uniform time scale of for which you can maintain this coherence, was pushed to as long as 6 seconds in this work by Jeller and Dave Lee at Cornell. What they are showing you here, and which is embodied in the theory and the experiments earlier in Moscow, in which the frequency of precession, which is uniform throughout this volume, is swept from one value to another as the domain wall moves upwards, and the frequency of precession is determined by the position of this domain wall in a gradient field. Now I want to come back to the beautiful experiments done in Finland, in which two of these Magnon BECs, as they're called, are coupled together, where in addition there's an influence, a trapping, if you wish, that's associated with the free surface of helium-3 in a narrow cylinder. And in fact, in this recent work, the AC Josephson effect coupling between these two condensates has been observed. But that's not all. In the Lancaster group's work with Sean Fisher and colleagues, it's been shown that coherence times can be achieved much longer than 6 seconds. In fact, you can see here some measurements as a function of the field gradient that's imposed that can achieve several hundred seconds of coherence. That's really mind-blowing. And they claim, actually, that at lower temperatures, it's possible to exceed 1,000 seconds of phase coherence, that is a quantum state with T2 of 1,000 seconds. That's really amazing. And it suggests the possibility of using that phase coherence of a macroscopic number of nuclei as a detector of the putative axion wind, light mass dark matter. Now I come to discussing confinement, superfluid helium-3 in confinement. And I'll start with silica aerogel. Actually, there are two kinds of aerogel that I want to discuss here. One is silica aerogel, another is a very anisotropic aerogel called nathan. And finally, I'm going to discuss slabs of helium-3 as another form of confinement of the superfluid. So here's a picture of aerogel from an SEM picture. They look like an amazing complexity of little silica balls about 3 nanometers in size. Nonetheless, the long mean free path of superfluid helium-3, which is embedded in this structure, averages this out. And you get very sharp thermodynamic transitions for helium-3 in this environment. And here is the discovery of superfluid helium-3 in silica aerogel by the Cornell group. This is Jivak Parpia's group and Northwestern as well. In the first case, it's the superfluid density that's measured by a torsional oscillator. And in the second case, it's NMR frequency shifts. And just as they were observed in the pure helium-3 case long before, there is a classic signature of the onset of superfluidity. But I should add, rather suppressed from that of what was expected in the pure helium-3 case, both for the superfluid density as well as these frequency shifts. And the latter, the frequency shifts of the NMR spectrum, scale as the gap squared. In addition, the heat capacity, measurements of the heat capacity in the same environment of helium-3 in the silica aerogel show a suppression of the transition temperatures as a function of temperature. And in particular, that the jump in the heat capacity is pushed down here. I'm showing it's about a factor of 2. And interestingly, to conserve entropy, not having gone down to rather low temperatures, but nonetheless to conserve entropy, the prediction is that there has to be a limiting value for the heat capacity scaling with temperature rather than going to 0 as might be expected. And that limiting value corresponds to the entry of bound states. And in the theoretical calculations of the density of states, here again by Jim Sauls with Priya Sharma, they show the low-lying density of states associated with these bound states. Now, what about the nature, the symmetry? I've emphasized the importance of symmetry and the identification of symmetry in the superfluid phases. And well, now we have a different kind of superfluid phase, and you might ask, well, what kind of superfluid phase is it? And of course, you're going to see here that it's blue and it's B. Now, that comes from zero field measurements. And in my group, Guillaume Gervais and others in my group showed that this was the phase diagram. The actual delineation of what the phase diagram transition temperature is from normal to superfluid is a collaboration, if you wish, between the Northwestern and the Cornell groups in nice agreement. But it's interesting already to note that there's no A phase window up here. And that's in part because there's a suppression of the transition temperature by some amount, not a lot, but a certain amount, a significant amount. And as I had mentioned before, that strong coupling is reduced as you reduce the temperature. And so therefore, the A phase, which exists in pure helium-3 as a consequence of this strong coupling, that's gone. And so what you're left with is just the B phase. Now, we found that at Northwestern that we could create this, we grow silica aerogels, and we can grow them with which are stretch. Now, stretch is just a description of the radially shrunken silica aerogel away from its boundaries, and you can cut out a piece and measure the phase diagram, and the phase diagram pressure versus temperature has turned from blue to red. In other words, it's all A phase. With the slight exception that there's another phase transition which gives an A prime phase. And as we've concluded since that time, that this is entirely the A phase. The distinction between these two regions of A phase is the following, and it's shown in terms of frequency shifts, which I've said before is a measure of the order parameter amplitude as a function of temperature. And depending on the orientation of the angular momentum, with respect to the anisotropy axis imposed on this aerogel by stretching, the frequency shifts show a sharp change, and that sharp change is at a given temperature is where these open squares are delineated, and the orientation of the angular momentum relative to the anisotropy axis is parallel in this region and perpendicular over here on the left. So what has happened is the angular momentum decides to flop from being parallel to the anisotropy axis to perpendicular to it at a well-defined temperature. Let's call that temperature Tx. Now, it's also possible to compress the aerogel, which is kind of the opposite, if you wish, as far as strain is concerned, to produce a rather perhaps surprising result that the phase diagram becomes the B phase. It stays the B phase, but it's an anisotropic environment. And the frequency shifts that you can measure in that B phase show on decreasing the temperature an onset of frequency shifts to the right here. And then bingo, there's something happening at a temperature Tx. Oh, it's very similar to the behavior that was observed in the A phase for a stretched aerogel. And if you combine the Tx versus relative to Tc from both, you can see that they're rather consistent. So this is a measurement of the discrepancy of Tc minus Tx normalized to Tc as a function of pressure. And you can see that A phase and B phase are essentially identical. So this orbital flopping is consistent between the two, with one important exception. In the A phase, the angular momentum is parallel to the anisotropy axis, close to Tc. And just the opposite, or 90 degrees with respect to that, it's parallel to the anisotropy axis at low temperatures. That's just the inversion for what you have in the A phase, and that's a very interesting phenomenon. And the way to explore that phenomenon that we've chosen is to do numerical simulations of anisotropic aerogel. This, as far as I'm aware, this is an attempt which is a little bit difficult. Here I'm showing for 100,000 particles. The engine for the simulation of diffusion limited cluster aggregation, which has been performed in a number of different laboratories. But for anisotropic aerogel, you just have to change the time step in one direction. And the engine for that was created by Josh Simon, who's a high school student. Well, he's going to be at MIT next fall. But he did his work for several years in my group as a high school student, and he was helped substantially by my other graduate students in the group. And you can go to Man Nguyen's poster in the E session if you want to learn more about this. I'm going to tell you a little bit nonetheless, and that is from the calculations of the, over here on the left at the bottom. Take a look at that. This is a three-dimensional view of 100,000, this may be 40,000 actually, particles, silica particles that have diffused and aggregated. And you can project in either the XY plane or the XZ or YZ planes what that looks like. And if you do so, you see for an isotropic aerogel, that is where the time steps are the same in all three directions. And then you see more or less the same thing in each of these faces. However, if you go over here to the right-hand side, and in this case, the time step is smaller along the z-axis, there's no question that in the XY plane, you see a random distribution of the projected projection of the silica particles in the numerical simulation. And then you see gaps appear in the ZX and ZY directions. And this cartoon captures that, in which the, say, strands, if you want to call them strands of aerogel, are formed randomly in various planes with a gap in between them, shown explicitly in the numerical simulation. It's just the opposite for the so-called pneumatic case. And then now you might wonder, how does that compare with experiment? And here we have an answer. This is compressed aerogel, and this is stretched aerogel that I've shown you before, and there has to be a reason why I can say the experiment and the numerical simulations are connected, and that comes from the next slide. But I'd like to at least mention here that it's a little non-intuitive that you'll form sort of a pneumatic structure of these strands by making the time step longer along the z-axis. It may be even counterintuitive. And the result here, the proof of this comparison, comes from an analysis of the numerical aerogel, where the team has calculated the structure factor, which is the Fourier transform of the pair correlation function. And you can compare that directly with the small angle X-ray scattering. And for an isotropic aerogel, numerical aerogel, or from an isotropic experimental aerogel, you can see that we have nice circular symmetry in the diffraction of the X-rays and the behavior of the calculated structure factor. However, in the anisotropic aerogels, the identification of this horizontal intensity in the structure factor corresponds rather closely to the compressed aerogel, and that's the reason why this pneumatic case we're associating with compressed aerogel, interestingly. And just the opposite. For the planar aerogel, the numerical calculation shows, again, this stripe of strong scattering, and this is in the long distance limit. I mean, close to small q, then you're sampling the long length scales aspect of the problem. But also interesting is that at shorter length scales, which is the outer region here, you have just the opposite effect. It's I think, pretty clearly indicated here in this upper middle calculation of the calculated structure factor. You see this ellipse shape is just the opposite to the long length scale behavior, which is shown for small q to be perpendicular to it. And we believe, although I have not yet published, that this is strongly related to the orbital flop that we've observed in both phases. Now, the naphthalene aerogel that I've mentioned, that was discovered by Dmitriev in Moscow, has stabilized the polar phase, which is a new phase not observed previously. And the naphthalene aerogel consists of luminous strands. It's obviously anisotropic. And I'd like to just go back a little bit beyond my discussion of what the results are in this naphthalene aerogel. I'd like to go back a little ways to the prediction by Volovic and Miniev back in 1976. They predicted the existence of a half quantum vortex. They received the Onsacker Prize for that from the American Physical Society. And also another prediction which took place, which was motivated in part by our interest in anisotropic aerogels by Aoyama and Ikeda, who said that, well, the polar phase really should appear in that case if you have sufficiently anisotropic aerogel. Well, here we have it. And indeed, the measurements of the existence of superfluid helium-3 in that environment are demonstrated, and indeed the discovery of the polar phase took place. And that's determined from the frequency shifts of the NMR. And the resulting phase diagram of these, shown by the red solid data, is in close agreement to the theoretical calculations just recently published by Regan, Wyman, and Sauls for the existence of these phases between normal polar phase and the polar distorted chiral phase. And even further than that, and also of considerable interest, is the collaboration between the Moscow group and the group at Aalto University in Finland, Auti et al., of a half quantum vortex. Now, that's why I started out this discussion with prediction by Volovic and Miniev. And in the theory recently published, indeed, stability of half quantum vortices in pairs shows up. Here, I think they're separated by something on the order of a micron. There's also the existence of the half quantum vortices in this polar distorted chiral phase. Now, the other form of confinement that I had alluded to that's of some interest today is that of very thin slabs. The story actually began with Freeman, Richardson, Germain, and theorist Erkki Tyyneberg. And the experimental arrangement was to take 3,000 mylar sheets and stack them up with small spacing determined by little glass beads. And I think this work of Freeman et al. Motivated Vorontsov and Sauls to do calculations of what you would expect in a narrow slab like this one between the mylar sheets. And I would also say that some work on extremely thin films of the superfluid density was reported by Zhu and Crooker, and both of these experiments motivated some of this theory. And here's the result back from 2007. And that is, what I'm plotting here is an experimenter dream, that is the thickness of the slab as a continuous variable. The experimenters have more difficulty with that. And the phase diagram indicating what phase you would have in the as a function of temperature. And there's an A phase for small separations, small d's, and for larger d's, then there's a B phase. And interestingly, there's both a reentrant form of this phase, a very interesting reentrant form here as a function of the spacing. Also, there's an instability in the B phase to a new type of phase, which is called the stripe phase, where translational invariance is broken. Now, there's a rich history of investigation in the Royal Holloway group of John Saunders, Leviton and et al., in particular, both here in 2013 and in subsequent work that I've indicated here in 2019, and then finally, just recently in 2021. Here, the Wyman and Sauls calculation, now in the more experimentally addressable phase diagram of pressure versus temperature for a fixed D shows a swath of blue, which is their calculation of the broken translational invariance of the stripe phase. And the calculations that were done in 2013 from the Royal Holloway group show that there is certainly a phase boundary between an A-like and a B-like phase, but the evidence for stripe was not so strong. But then, even theoretically, that was probably not expected, at least at this pressure. These are low pressures from 6 bar to 0. However, in their more recent work, there's an interpretation that they have a pair density wave, and evidence also for the pair density wave from the University of Alberta group has come from the use of Helmholtz resonators, in contrast to the beautiful NMR measurements using very high resolution squid NMR techniques. Complementary to that, as I'm saying, the Helmholtz resonators also have high resolution, and they've done measurements in 3 sets of slabs. And they also give some evidence for an intermediate phase, or they give some evidence for an intermediate phase and argue that this could likely be a pair density wave. And lastly, in just recent work from the Royal Holloway group is this careful work by Petri Heikkinen and colleagues in which the boundary conditions of the slabs is controlled wonderfully from diffuse to specularity and then fully specular. This treatment of the surfaces is truly an important aspect of the theory, and is certainly also an aspect of the experiment. So I'm almost finished. I was going to end by some future prospects. I was just being a little whimsical, if you wish, in some measure, that some of the future prospects, such as what I had mentioned earlier, that perhaps we could harness the coherent states of the HBD as a dark matter detection scheme. And I'd be willing to say a little bit more about that if you wish. And then I also wanted to point out the prediction of anomalous thermal Hall effect that began with the chiral superconductor of Goswami and Nevedomsky at Rice University, and they predicted that in the presence of chiral superconductivity, that you would expect a Hall effect, that is, you have a transverse thermal gradient to the main thermal current. And Jim Sauls with his postdoc wave, they did the same thing for helium-3 and for superconductors, but with the added interesting feature that if you put impurities into the system, that is, let me say, silica aerogel, for example, then it should be possible to see this anomalous effect, which is almost 2 orders of magnitude increase in the transverse thermal gradient. And that comes from the fact that you have a plethora of Andreev bound states associated with these impurities, and they integrate, as opposed to just edge currents, which are relevant to the pure chiral superconducting case. And finally, I think I'm probably running out of time, but finally, I have another wild speculation. Well, not another wild, so this one's a wild speculation that I recognize that solid helium-3 is in an antiferromagnetic state at low temperatures, meaning below 1 millikelvin, and that the entropy of solid helium-3 decreases like the 4th power of the temperature. Now, liquid helium-3, if you apply a magnetic field above half a Tesla, then liquid helium-3 will have an entropy which decreases as the square of temperature. And consequently, the solid helium-3 entropy should drop below that of the liquid helium-3. This is sort of an inverse Pomeranchuk environment. Consequently, with a sample of, say, pure solid helium-3, if you were to melt it, following kind of the procedure of Castan-Nozière, that you should get cooling. And furthermore, you might get cooling with if you start with a very high magnetic field to produce essentially 100% polarized superfluid, which could be a very interesting venture for the future. And with that, I would just like to thank my list of students and collaborators over the years, and I'm just restricting my thanks to them here. They have shown their names in green. There are, of course, many people I've mentioned in the references who have contributed seminally to the aspects of the beautiful aspects of the properties of superfluid helium-3. And in particular, I want to thank Ambrish Ghosh and his collaborators in organizing this conference and this particular session for you today.
Thank you very much, Bill, for an extensive and very clear presentation. And also for your comments about future prospects. So there are a number of, let me ask you to say a few words while we're waiting for some questions to come in. We are overrunning by a few minutes, but I don't mind, and I hope nobody else does, actually. So there have been a number of presentations on Friday to do with using helium systems for dark matter detection. Of course, one is which hasn't been presented so far is just the idea of using it as a calorimetric detector in a spin-sensitive way. So the idea that the HBD could be used to detect axions, which will be a different class of particles, it's the one that calorimetric detection will be sensitive to, is very interesting. Particularly if you're going to go to the trouble of putting a dilution refrigerator in a mine, it might be nice to look at two kinds of dark matter. So could you say a little bit about the, since there's such a vast number of orders of magnitude in the possible mass range, and these are all obviously theoretically motivated. So a few words about the axion detection would be, I think, interesting to this audience and the more general, wider audience. If you
would. All right, I'll give this a shot. My collaborator in this regard is Yoni Khan at the University of Illinois. He's a theorist. So he pointed me towards an archive, a preprint from the Casper group. Casper group is pursuing dark matter from the perspective of polarized xenon. But he pointed me to this article, and it makes it rather clear that according to the theory of the axion in very light mass, now the frequencies of precession that we're talking about are very low, and that basically defines the mass range. I mean, they're extremely low. So there's a very light mass axionic, far from WIMP. And in this limit, the de Broglie wavelength is kilometers or more. So what you have is a wind. Yeah, they can describe it as a wind. And the prediction is, or the calculation is, that the axionic wind has a direct coupling to the nucleus. And it has unusual properties, but you can therefore calculate what is the effect of this effective magnetic field which comes from that coupling. And then that would be observed in the nuclear spin precession, for which I have a little numerical simulation that I could show. But I'll just say in words that you would expect perturbation of the precession when the frequency of precession is modified to, or naturally modified, as Jeller and Lee has pointed out, for example, as naturally modified to pass through the mass of the axionic matter.
Okay, thanks. I see as yet no questions, no further questions from the floor.
Basic chart upvoted, that's why it's up there.
Sorry, Ambrish, could you say that again, please?
Choi and because it's upvoted, it's the top of the Q&A box.
Okay. I couldn't. Oh, here we are. Johannes Polanen has an interesting question, which maybe I'll ask on his behalf. Is there any scenario where you get F-wave pairing superfluid with the typical superfluid phases of helium-3 suppressed by confinement?
You mean where the F-wave pairing would survive yet, but P-wave pairing would be suppressed specifically? And that sounds like an amusing idea. I have nothing to offer to be able to say that's viable. I think if you put superfluid helium-3 in a non-bulk environment, then you're going to ultimately torture it enough to suppress it in its transition temperature and to favor one or the other. That's going to be quite an interesting job. Perhaps our theoretical colleagues will have a suggestion there.
Yeah. Of course, nobody's yet gone into the truly 2D limit, so that's another interesting place where something.
Indeed.
Yeah.
Indeed.
I'll make some concluding remarks, which I will stop making if a really interesting question materializes. So just to say, I think we've had a really interesting set of talks, which graphically illustrates the profound contributions that helium physics can make to a broad range of disciplines based on the unique properties of helium. And we've got connections with topological superconductivity and unconventional superconductivity more generally, and also the work on electrons on helium, on charges interacting with helium, pertains very strongly to the work on quantum computing systems based on electrons on various substrates that we've heard about earlier in the week. As far as the fractional quantum Hall effect is concerned, maybe I'll just make one point. That there are a number of people in the community interested in the possibility of cooling electrons to two-dimensional electrons in a heterostructure to below 1 millikelvin. So far as I understand it, typical lowest temperatures are between 5 and 10 millikelvin. So I might ask Joinendra if he would like to comment on his perspective on the interests of taking the 2DEG below 1 millikelvin.
Yeah, I can only say that whenever the sample quality has improved or the temperature lowered, there have been surprises in the field. So there are many fractional Hall states which seem to be incipient but not yet fully developed, and I think cooling the temperature further could open up possibilities for many other fractional Hall states. So I think that would be, I mean, I do not know what is the obstacle in reaching below 1 millikelvin temperatures in heterostructures.
Yeah, well, there's a lot of work going on this subject within the European microcarbon platform. So I think there's some progress that will be announced relatively soon on that. So I think it's interesting to hear your views on it and the open questions that still remain. So I think without further ado, before I hand back to Ambarish, on behalf of the assembled company, I'd like to thank all of our speakers again for giving us such a broad overview of the possibilities of our field. Thank you very much. And Ambarish, over to you.
Thank you. Actually, I would request the speakers to please come on stage if possible, just to keep your. We would like to take a picture. Professor Kono, oh, fantastic. Good. Thank you. Thank you very much. And before we break for the day, I would like to thank the session chair, Professor John Saunders, for moderating this session. It was very successful. Thank you so much, John. Thank you so much.
Pleasure.
And I wanted to remind all the conference attendees that tomorrow is a holiday, and we are going to meet again Monday, 4:30. Thank you all, and have a good weekend. Bye-bye.
Bye-bye.